Today we're going to move ahead into Chapter 2, which is looking at a physics and chemistry review. Now I know for most of us that physics and chemistry aren't anybody's favorite subjects and don't really rank up there too high in terms of things we'd like to talk about and discuss. But as we look at biology, we have to realize that living organisms are composed of chemicals. We do survive in that physical or that natural world around us. And so if we're going to understand life and living organisms and how life continues, we have to understand some basic physical properties and also certainly some chemistry to be able to put that together. And so Chapter 2 is dealing with some basic review. Now for many of you this may be review, maybe you've had this in a high school biology or a high school chemistry or physics class, but I know for many of you this probably is not a review and it's new material. And so I want to take some time, just go over some of these basic ideas so that we all have a good firm foundation as we move forward throughout the semester. And we'll start with physics first. My version of Physics 101 is actually pretty brief because as we look at living organisms, there's really only two major topics that I want to make sure we hit on. That first topic is energy. And technically defined, energy is anything that enables an object to do work. And as we think of life, we know certainly living organisms have to be able to acquire energy, to spend energy, to save up energy. So a very, very important concept as we look at living things. Now you may recall that there are two basic forms that we may see energy in if we think very big picture. The first form of energy is called potential energy. Potential energy represents energy that's stored up. And so it has the potential to do work, but right now it's not doing anything. And our classic example of potential energy is we think of something like a battery. It's stored up energy, it's energy there if we need it, but if we don't need it, it's going to be saved up. Our other major form of energy then is kinetic energy. Kinetic energy represents energy in motion. So that's energy that actually is currently doing work. And we think of kinetic energy, think of your car engine. When your car engine's running, it represents kinetic energy. It's going to make that car move. When we think of these properties then compared to living organisms, our potential energy source typically is going to be chemicals, things like food. Food contains lots of potential energy in it. We can convert that potential energy then into kinetic energy when we need to have energy for metabolism or growth or repair and so forth. Now, another important term here that I want to mention as we start thinking about energy is temperature. And temperature is a measure of how much kinetic energy is in a system. And we'll deal with this certainly a lot in lab this semester. And so as we think about temperature, think energy. We're really measuring how much energy is present. And so on a really hot day, the temperature is high. That means there's more energy in the air. On a really cold day, there's less energy in the air. And so that temperature then drops. Now physicists explain how energy works by the laws of thermodynamics, and there's two basic laws of thermodynamics. The first law tells us that energy can neither be created nor destroyed. And so we can't make energy, we can't get rid of energy or make energy disappear. Now we use terms all the time like we're going to use up energy or I'm going to burn some energy and so on. But when we use those terms, what we're really doing when we use up or burn energy is we're simply changing the form of that energy, changing that energy from maybe stored up energy in terms of food into kinetic energy. And so as we think of living things in our planet, we don't destroy or create energy. We're simply changing energy from one form to another. And certainly as we look at living cells and we look at life in general, energy is constantly being changed from one form of energy into another, from stored up to kinetic energy, maybe from one chemical into another chemical form of energy. Our second law of thermodynamics then, explaining how energy works, is going to deal with this idea of energy changing forms. If living things are changing the energy from one form to another, what happens as that energy gets converted? And the second law tells us that every time we do change that form of energy from one type to another, the amount of usable energy is going to decrease. So some of that usable energy is going to be lost. Now we're not destroying that energy. It's usually going to be converted to heat. And remember we said heat and temperature is a measure of kinetic energy. And so heat is a type of energy, but it's not a usable energy. As living things, we can't store up heat and use heat later for energy. And so when we change that energy from one form to another, it's never 100% efficient. The amount of usable energy that we have is going to go down or decrease every time we change forms. And again, as living organisms, we're constantly changing forms, we're constantly spending energy. And so as a living organism, we're all very highly structured and organized, very, very complex. And it takes a lot of energy to maintain that structure, to maintain that complexity. And so this is one of the reasons why, as living organisms, we have to have this energy input, that life cannot exist without acquiring some sort of energy just to maintain our current structure. It's going to require even more energy than to spend energy on growth or repair or reproduction and so on. And so this is sort of one of the reasons why we see energy as such an important aspect to living things, this second law of thermodynamics. Our second major concept concerning physics is the concept of matter. And if we define matter, matter is simply anything that has mass and takes up space. And so anything that you can think of, whether it's the desk you're writing at, it's the air you're breathing in, maybe it's the chemicals that make up your cells, all of that represents matter. Now physicists tell us, well, technically if we were in the middle of a black hole, that might not be matter. But again, as living things, anything we can think of really represents matter. And I'm sure you're familiar with the three different states of matter. We can have a particular type of matter or chemical that can be found in the solid form, the liquid form, or the gaseous form. So if we take a look at our three states of matter, solid, liquid, and gas, and compare what are some different basic chemical properties of those three different states. So if we look at our chart here again, we'll look at a solid, a liquid, and a gas. One of the main characteristics that's important or different for each of these different states of matter then is density. And density just refers to how tightly packed are the chemicals. If something is very dense, the chemicals are tightly packed together, there's no space, they're kind of smashed together. If something has a low density, there's lots of space between those molecules. The chemicals are going to be spread out. And as we look at our different states of matter, solids are going to have the highest density. The chemicals are packed together very, very tightly. There's not much space. Liquids, the chemicals are going to be spread out a little bit. And then gases have the lowest density. There's a lot of space between the chemicals in a gas. Our other main characteristic then is kinetic energy. How much energy is in motion in these different chemicals. And all chemicals do have some amount of energy. And so out there in nature, all chemicals contain some kinetic energy. Solids contain the least amount of kinetic energy. So if we think of the chemicals in a solid, they're very dense, the chemicals are packed tight together, and they're vibrating. They're moving a little bit because they have some energy, but they're not moving very much. The molecules in a liquid are going to be spread out a little bit, and they're going to have a little bit more energy, so they're going to be bouncing around a little bit, and then gases have the most amount of kinetic energy. And so these represent molecules that have a lot of space between them. They're moving around and bouncing around very, very quickly. And in fact, gases have enough energy in their molecules that they can move up. They have enough energy to combat the force of gravity, which is why gases fill up a three-dimensional space. Now, if we think of converting from one to another, if I have a liquid like water and I want to convert it to a gas, I have to heat it up. And basically, by heating it up, I'm adding kinetic energy to it. And so if I add energy to a liquid, I may be able to convert it to a gas, converting water to steam if I boil it, for example. Or we can move the other direction, and I convert my liquid into a solid by taking energy out. And so by altering the amount of energy in our state of matter, we can convert it from a solid to a liquid to a gas, or vice versa. Now, as we move along toward our chemistry review, we're going to spend a little bit more time certainly on chemistry than physics, because chemistry is so intimately entwined or tied to life and living organisms. And we live really in an amazing time today that we can study organisms at this very specific chemical level. And the more we learn about the chemistry of life, the more we see that an organism's ability to metabolize, to grow, to reproduce, to even just be healthy really does rely on basic chemistry. And everything an organism is or can do often is tied directly to chemistry. And so we're going to spend some time certainly looking at chemistry. And as we spend the semester looking at not just chemistry but life in general, we're going to take what's called a reductionist approach. And this is really typical in science. If I was trying to study your body, for example, and understand exactly how all your different cells and so forth work, it's an immensely complex task, and I probably would never get very far. And so in order to understand a whole big picture, what we do is, with this reductionist approach, is study small parts. We're going to start small and study the chemicals. Then we'll put those chemicals together and study how a cell works. And then we can put those cells together and study how the whole organism works. And so in general, we are going to take this reductionist approach. We're going to start studying small at this chemistry level and then gradually build toward larger and larger structures within living organisms. So as we look at our chemistry review, the most basic place to start then would be this idea of these chemical elements. And a chemical element, if we look at our official definition here, is any substance that cannot be broken down to other substances by ordinary chemical means. And let me say that again as we kind of let that percolate a little bit. A chemical element is a substance that cannot be broken down to other substances by ordinary chemical means. And so a chemical element is this unit out there that is very pure, and if we try to break it down, we're not going to be able to do it. Now, we have to throw it by ordinary chemical means on there because obviously in today's world, if we throw something in a nuclear reactor, we can change just about anything. If we conceptually think of what does this definition mean, what really is a chemical element, we can think of chemical elements as basic building blocks. There are over 100, and certainly in your book you'll find a chart of the different chemical elements, and each chemical element has slightly different chemical properties to it. And so each of these different elements represent slightly different chemical building blocks that we may combine in different types that are going to give us chemicals that have different chemical properties. And again, if we look at our universe and our planet, there are over 100 different chemical elements that make up all the different structures that we find. Now, as biologists and studying life, we're not going to have to worry about all 100, because if we were to chemically analyze your body, for example, we would only find about 25 of those different elements making up life or living organisms. But the reality of the situation is we're not even going to have to worry about 25 of these, because if we do chemically analyze a living organism, what we see is 4 of the elements, oxygen, carbon, hydrogen, and nitrogen, make up over 90% of most living things. And humans in particular, those 4 elements, oxygen, carbon, hydrogen, and nitrogen, make up over 96% of our body weight. So if we look at a chart here, we can see the symbols there, O, C, H, and N for those 4 elements, making up a little over 96% of our weight. If we look at some other common elements we find in our body, things like calcium and phosphorus and sodium and chlorine, they make up relatively substantial amounts. And then there's a whole list of trace elements, things that we need but in very, very small amounts, like boron and iron and fluorine and selenium and so on. And so all those minor elements would represent trace elements that we need. And these are the types of things that you might find, for example, in a multivitamin, things that, these trace elements that we need. Now, as we look at our chemical elements, an atom represents the smallest amount of an element that we could have. So we could have 1 atom's worth of carbon, or 1 atom's worth of oxygen would be the smallest we can have. And so for each of these basic elements, we can look at an atom of that element. And if we were to compare an atom of carbon, for example, to an atom of oxygen or an atom of hydrogen, what we see is all the different elements or chemical building blocks are made up of the same basic components. And these are probably things you're familiar with. Things like protons, neutrons, and electrons comprise our basic atoms. And so we would call these atomic particles, the protons, neutrons, and electrons, because they make up our atomic structure. Now, what makes oxygen chemically a different building block or element than carbon or nitrogen is simply, well, how many of these basic atomic parts do we find? How many protons, neutrons, or electrons make up the atom is going to give each element then its distinct chemical properties. And so let's take a look at atomic structure. This cartoon just is a typical drawing of what atoms would look like. If we look on the left there at the helium atom, the protons and the neutrons are contained inside the nucleus, and so we can see them there in the center, and nucleus just means center, and so it's going to be the center of the atom. The electrons, by comparison, are much smaller, and they orbit or circle the nucleus. And so on the very left, we see our 2 electrons there, and they're connected with that line just showing the orbit or the path they take. Sometimes when we see atoms, they're drawn with a little cloud around them, indicating that those electrons are constantly moving, and so we never really know where the electrons are at. They're somewhere in that cloud. They're somewhere moving around. And again, if we compare helium and carbon, they're both made up of protons, neutrons, and electrons, but carbon has more of those particles, 6 protons and 6 neutrons in its nucleus, and then 6 electrons orbiting the atom. And I do want to point out with this chart, we don't always have the same number of protons, neutrons, and electrons in an atom. In the case of helium and carbon, they're the same, 2 of each in helium or 6 of each in carbon, but that's not always the case. It really just depends on the specific element that we're looking at. We'll start at the nucleus, the center of the atom, and look at atomic structure. And again, our 2 main particles here in the nucleus are going to be the protons and the neutrons. And so if we start with the protons, protons have a positive electrical charge, or a plus electrical charge, and they also are relatively large, and so they're assigned a mass of 1 atomic mass unit. So they're positively charged, and they're pretty big. And if we look at a periodic chart, we typically see numbers associated with each element, and the largest number on the chart represents the atomic number. And the atomic number simply tells us how many protons are in the nucleus of an atom. So for example, carbon has an atomic number of 6. We know it has 6 protons in its nucleus. Oxygen has an atomic number of 8. It has 8 protons or plus charges in its nucleus. And it's this atomic number, or the number of protons, that is unique for each element. And so we've got over 100 different elements or chemical building blocks. Each one has a different number of protons in its nucleus. Our other major component then of the nucleus are those neutrons, and as their name implies, they're a neutron, they're neutral. They have no electrical charge. They're completely electrically neutral. They're very similar to protons, though, in size, so they have a mass of 1 atomic mass unit. And if we look at our protons and neutrons together, they make up the bulk of the mass or the weight of the atom, and so that's our atomic mass. And if we look at a periodic chart, we typically see two numbers associated with each element. The largest number on the chart is the atomic number. Then usually the smaller number, oftentimes it has decimal places associated with it, is the atomic mass. And we determine the atomic mass by adding the number of protons and neutrons together, and that's going to give us the weight of that atom. So if we look at atomic masses, for example, of carbon, it has an atomic mass of 12. It's got 6 protons plus 6 neutrons to give it that 12. If we look at something like chlorine, it has an atomic mass of 35. It has 17 protons and 18 neutrons to give it that 35 for its atomic mass. Now, as we look at that chart, for example, with carbon, it tells us that the atomic mass is 12. That mass that it gives is for the most stable or the most common form of carbon, but all atoms of the same element don't necessarily have the same mass or the same size. And an isotope then is when we have two atoms of the same element that have differing atomic masses. And those differing atomic masses are always going to be due to different numbers of neutrons. And so if we add or take away neutrons from the nucleus, we can change the weight of the atom or convert that atom into an isotope. Now, isotopes will have the same exact chemical properties as its more stable form. And so if we add or take away a neutron while we change the size of the atom, we don't change the chemical properties at all. Now, many isotopes we know are radioactive, and this is where radiation kind of fits into the picture here, because isotopes are often unstable. And so that isotope will break down and lose neutrons, and as it loses neutrons, it'll convert back into its stable form. And when that neutron is lost, a lot of times an atom will give away a lot or lose a lot of energy, and that energy lost is radiation, and it's that large burst of energy that's lost that could be harmful to a living organism. So, for example, if we use carbon as our example, since it's so common in living organisms, our most common form of carbon is carbon-12 with 6 protons and 6 neutrons. But as carbon gets exposed to high amounts of energy, whether it's in the mantle of the Earth as it undergoes melting due to volcanic activity, or maybe it's carbon high up as carbon dioxide in the atmosphere gets bombarded with UV radiation, that carbon may be converted into carbon-13 or carbon-14 isotopes, having an extra neutron or even 2 extra neutrons added. Now that carbon-14, for example, though, is very unstable, and over time it will gradually lose 1 neutron and then lose a second neutron and convert back into carbon-12. Today we use isotopes for several applications and take advantage of this process of the isotope breaking back down into a stable form, and in particular isotope dating, or you may have heard it referred to as carbon dating, is an example of that. And so in carbon dating, or other isotopes may be used for things that are much, much older, we know that that stable isotope is gradually going to break down into its stable form over time. And we can measure how quickly an isotope breaks down into its stable form by what's called the half-life of that isotope. And so the half-life represents how long does it take for half of that amount of isotope to break down into the stable form. And so, for example, if I have a gram, let's say, of carbon-14, its half-life is 5,700 years, meaning it would take 5,700 years for that gram that's all carbon-14 to be converted into half a gram of carbon-14 and half a gram of carbon-12. So half of it would break down back into its stable form. And we can use isotopes for dating because this half-life, for example, this 5,700 years for carbon-14, is going to break down at this consistent rate regardless of whether it's in the sun or in the shade, whether it's hot or cold, whether it's buried deep in the ocean or whether it's up near the surface. That isotopes break down at a consistent, steady rate no matter what. And so that's what we utilize then to date things, is this half-life. And so when we want to date things, when we want to date an object, we're going to date it based on its ratio of carbon-14 to carbon-12. And so let's take a look at a specific example here. Let's say we find a bone, and that bone, we're going to measure its carbon-14 carbon-12 ratio, and that bone has about 1/4 as much as of the carbon-14 that we would normally find out there in nature. And so we could ask the question then, how old is that bone? Can we date that bone? And the way we're going to figure this out is if we look at your bones today, since you're alive, your carbon-14 to carbon-12 ratio will be the same as what we would find in the environment, because you're constantly taking in carbon and exchanging carbon with the environment. Your ratio is going to be exactly the same. But when you die, you're not going to take any new carbon in. But that carbon-14 in your body is going to gradually start converting back, because it's unstable, into carbon-12. And so over time what we're going to see is your carbon-14 to carbon-12 ratio, the older your structures are, the less carbon-14 we're going to have as it gradually breaks down. And so in this case, because there's 1/4 as much carbon-14 as we would normally find in nature, we know that that bone is 2 half-lives old, that it took 1 half-life to go from the normal carbon-14 amount to half as much as in the atmosphere, and then 1 more half-life to convert that half into 1/4 as much. And so in this case, we would know that this bone is about 11,000 years old, since it has only 1/4 as much as a normal carbon-14 as we would find in the atmosphere. Another common application we have for isotopes has to do in the medical field, and certainly a lot of common medical applications today take advantage of using isotopes to help diagnose and treat various diseases. And so, for example, things like PET scanners would be an example of something that takes an advantage. And that's what we see here in this picture is this PET scanner. This gentleman's being placed in the PET scanner. And the reason this works is because these isotopes release energy as they break down, and because they chemically behave just like the normal element, if I give you some of this radioisotope, whether it's to eat or I inject it in IV form, your body's going to process that chemically normally. But normally, we wouldn't be able to trace where those chemicals go. But because those radioactive isotopes give off a little bit of energy, we can give you a chemical with a little bit of this isotope in it. Your body's going to process it, and then we can track where does that chemical go in your body by following where is the energy in your body. And we can see then, is your body processing that chemical normally, or is there a metabolic problem, a medical issue? And so in this case, what they often do, and this is looking at some brain injury or brain damage, is they'll give an individual some chemicals to drink, usually involving some isotope, for example, like iodine, that's very low energy, so it's not going to be harmful to you. And then they'll give you a task to do, like reading or listening or writing, and then they're going to monitor, in this case, look at your brain and look for the energy to see if the chemicals are being processed and sent to the right portion of the brain. And if they are, then they know that the brain injury maybe is pretty mild, it's not a permanent problem. But if the energy doesn't end up in the part of the brain it's supposed to, then they know that maybe there's been some major trauma, and that's an issue that's going to have to be looked at. So the protons and neutrons make up the nucleus, one major part of our atom. The other major part then are the electrons. And electrons are going to orbit or circle the nucleus. They're very, very high in kinetic energy, so they're constantly moving. By comparison to protons, electrons have a minus or a negative charge. And we know that pluses and minuses are attractive, that opposite charges attract each other. So certainly these electrons are going to be attracted to the positive protons in the nucleus. Now electrons are extremely small. Technically they weigh something, they have a mass, but their mass is so tiny compared to those neutrons and those protons. That's why we don't count the electrons when we count the mass, because they're very insignificant in terms of size. Now because they're small and they're full of energy, they are in constant motion and they're constantly circling or orbiting around the nucleus. And the reason they don't just simply fly off into space because they have so much energy is that attraction to that nucleus that holds those minus charges close by. Now, if we look at the electrons and how they orbit or where they orbit around the nucleus, we see that all the electrons aren't just jammed in close to the nucleus, but instead they're typically arranged in several layers around the nucleus. And those layers are oftentimes referred to as shells or energy shells. And so if we take a look at the big four atoms here, the four most common atoms in our body, hydrogen, carbon, nitrogen, and oxygen. Now the most stable place for an electron to be is very close to the nucleus because, again, those pluses and minuses are very attractive. And so in something like hydrogen that only has one electron, that electron is going to be very close. It's going to orbit in this inner shell or this first circle. If we compare, though, for example, with carbon, carbon has 6 electrons. Now we're not going to see all 6 jammed in close around that nucleus in that first orbit. And the reason for that is, while it would be more stable to be close for those electrons because those pluses and minuses are attracted to each other, remember, our minus charges will react with each other, and like charges tend to repel. And so if I get too many minuses close to each other, too many electrons close by, they will repel each other. And so what we see is that first shell or that inner circle we'll only see 2 electrons. Any more electrons than that are going to start to move a little bit farther away, and they're going to be bumped out to the second shell. And again, that's sort of a compromise, so that the electrons are all reasonably close to the nucleus, but they're not so close to each other that they're interfering with one another. And so that inner shell, because it's so close to the nucleus, is a relatively small orbit or circle. It can only hold 2 electrons. The outer shell then can hold up to 8. And so any atom that has more than 2 electrons, the next group of electrons are all going to move out and fill up that outer shell. Now once that outer shell was filled up, if an atom had more than 10 electrons, let's say, then that 11th electron would move out to a third shell, and so on. And so all these atoms have several different energy shells. Now in biology, we're going to be dealing with atoms that only use the first 2 or 3 shells, and so we're not going to have to worry about anything more than those first couple of shells. Now the whole reason I bring up this idea of energy shells and, well, who really cares, where are the electrons located, is it turns out that's really important for the chemistry of an atom, and that atoms that have their outer shell completely full of electrons are very, very energetically stable. And so if an atom has an outer shell that is full, it will chemically not react with anything else. It will be stable. But if an atom has an outer shell that has a few electrons in it, but it's not completely full, then it tends to undergo chemical reactions. And so if we look at chemistry, many, many chemical reactions are going to occur as atoms interact with each other and either exchange or share electrons in an attempt to fill out their outer shell. Okay? And again, they're not doing this because they want to or they need to, but having a full outer shell is stable. And so when we mix things together, they will keep reacting until they reach a stable form, which in this case would be having an outer shell of electrons full. And again, as a reminder, that first shell is filled with 2 electrons. The second shell holds up to 8 more, and then that third shell typically will hold another 8. And those are the main levels we'll dealing with atoms that are found in living organisms. So atoms will oftentimes either give away or accept electrons as those outer shells are filled up. And if an atom gains or loses an electron, that creates what's called an ion. And an ion is simply an atom that has unequal numbers of protons and electrons. And remember, protons are plus charge and electrons are minus. And so most atoms, the pluses and minuses are equal and they cancel each other out. But in an ion, if I've got too many pluses or too many minuses, then the pluses and minuses will not equal or cancel each other out, and so we'll have an atom with an electrical charge. And so an ion represents either a plus or a minus charged atom. A negative ion would have a minus charge, and that would be an atom that has gained 1 or more electrons. A positive ion would be an atom that has lost an electron, that has given away an electron, and so it has more pluses than it does minuses, so it's going to have an overall plus charge. Now let's take a couple look at some examples here of these negative and these positive ions. Let's take a look at an example of a positive ion. And a good example of that is something like sodium, which is Na on the periodic table. Now sodium in its pure state is always going to have an equal number of protons and electrons. And its atomic number 11, so it typically has 11 protons in its nucleus. So it's going to have 11 electrons orbiting that nucleus. Again, if I have pure sodium. So let's take a look at that in terms of how the electrons are arranged. My nucleus of sodium here, the first 2 electrons are going to be in that first shell. They're going to be very close to the nucleus. Now once that's full, then the next electrons are going to move out to that second layer or that second energy shell. Remember, that holds up to 8. So now that's a total of 10 electrons. Sodium has 1 extra electron. It's going to have to move out to that third different layer. Okay? And so remember, having an outer shell of electrons is very stable. And so if I mix sodium with other atoms, it's going to either gain or lose electrons to fill up that outer shell. And if we look here at our diagram, the obvious response to sodium is going to be to lose an electron. Because if sodium lost that 11th electron, then its outer shell would be that second layer and it would be full. And so typically, if I mix sodium with other atoms, that's exactly what will happen, is it forms a sodium ion, because now my sodium atom has still 11 protons in its nucleus, but now it only has 10 electrons orbiting the nucleus. And so it's going to have an extra plus charge to it, and so we would write that as Na with a plus, indicating a sodium ion. And so while sodium in its pure state has an equal number of pluses and minuses, out in nature I almost always see sodium as an ion, because it's going to interact and lose that electron. By comparison, if we look at an example of a negative ion, that would be an atom such as chlorine. And chlorine has 17 protons, so it has an atomic number of 17, and in its pure state, again, it would have 17 electrons. So if we look at our diagram here, it's going to have 2 in its first shell. The next 8 electrons are going to move out to that second shell, and now it's got 7 more electrons left that are going to move out to that third shell. And so to have a full outer shell, the easiest thing, or the most common thing that will happen to chlorine, is it's going to gain an electron. Because if chlorine gains 1 more electron, now its outer shell would be full. And that's typically what happens. If I mix chlorine with other atoms, it's going to gain an electron, and it's going to form a chlorine ion. Because I've got 17 protons in the nucleus still, but now I've got 18 electrons. And so I've got too many minuses, I've got that extra minus charge, and so typically we would see chlorine as an ion with a Cl minus. So just to wrap things up today with our physics and chemistry review, again with physics we talked an awful lot about energy, both potential and kinetic. We also mentioned temperature as a measure of energy and those two laws of thermodynamics. And then we looked at matter, our three states, solid, liquid, and gas, and our characteristics of matter are going to be density plus how much energy is contained in those chemicals. And then we got into our chemistry review. We know that we have over 100 different chemical elements or building blocks, and each of those elements, the smallest amount I can have would be 1 atom's worth. And if we look inside of an atom, we see that it's made up of protons, neutrons, and electrons. The protons and nucleus are in the nucleus. If I change the number of neutrons, we make isotopes, and we talked about some applications of those isotopes. The electrons are going to orbit that nucleus, and as atoms gain or lose electrons, they might form ions, which are going to be a charged or plus or minus atom. I know that for some of you, some of this is review, and again, for others, it may be brand new, and I know that for some of this, it's kind of complex stuff. And so if you're struggling with some of this chemistry and physics, make sure you read over your chapter. Also, go online to the mybiology.com and look at some of the tutorials and do some of the practice quizzes so that you get familiar with this information.